Hello guys, this is Moksha Shah from TE Electronics. So today I'll be showing you all an experiment on practical differentiator. So first we'll be implementing a practical differentiator using op-amp OP07 and then study its frequency response. If I talk about the ideal differentiator, we have a resistance and feedback, but the reason for shifting to a practical differentiator is nothing but as we go on increasing the frequency, the gain also increases, because of which at higher frequencies the differentiator becomes unstable and causes oscillation, which results in noise. So to avoid that, we connect a capacitance in parallel with the feedback resistance, and to the input capacitance we give a series resistance. So if we talk about the calculations, given that FA is 1 kHz, that is the lower cutoff frequency, and FB is 10 kHz, that is the upper cutoff frequency. If I assume the C1 to be 6.8 nanofarads, the FA is nothing but 1 upon 2 pi RF C1. FB is 1 upon 2 pi R1 C1. So I get the values of R1 and RF accordingly. If I assume R1 into C1 is equal to RF into CF, then I'll get the value of the feedback capacitance, that is 0.68 nanofarads. If I talk about ROM, it is nothing but R1 parallel RF. So let's just open the LTspice and build the practical differentiator. So first I'll just remove the first part, so you can just go to the cut and remove it, then escape, then go to the components, click on voltage and place it over here, escape, and then right click on the voltage, go to the advanced, go to the sign, give the DC offset as 0, amplitude as 1.2, frequency as 1 kHz. I'm showing you at 1 kHz, then run. So at the input side you are getting a sine wave, and at the output side you should get a cosine wave. So yes, you all are getting a cosine wave. If I left click on V out, I'll just drag it to the peak values to get a V out voltage. So this is 1.185 voltage. To get the voltage peak to peak, we just multiply it by 2. So same thing I've done over here. The V input is 1.2 volts, and for peak to peak multiply by 2. I'm getting the V out value as 2.3. That is correct. Now gain is nothing but V out by V. So by that I've calculated the gain. To calculate the gain in dB, it is nothing but 20 log of V out by V in. So I've taken the different values of frequencies so that I can understand and to learn the working of a practical differentiator at a different frequency values. So I've highlighted the upper and the lower cutoff frequency. Now I'll be showing for the input square wave. So just I'll be opening the LTspice again. I'll go to the LTspice. I'll just cross this full screen, just right click again, click on pulse, and now this will be -1, this will be +1, the time delay will be 0, T rise is nothing but 0.001 micro, T fall will be same 0.001 micro, T on is nothing but 0.5 milli, and time period is double of it, that is 1 milli. Click on OK. To place it properly, just drag this and place it over here. Now run. Click on the input side. So yes, I'm getting a proper square wave, and at the output side I will get a alternating negative and positive spikes. So this is correct. This is about the input square wave. If we talk about the input triangular wave, just right click over here. First three values will remain same, and I'll just change the values of T rise, that is 1 milli, T fall will be same to 1 milli, my T on will go to 0, and T time period will be the double of T rise or T fall, so 2 milli. Click enter, just run. The input side will be the triangular waves, and the output side we are getting a proper square wave. So for the input triangular wave you are getting a square wave. Now I'll be showing you all the frequency response. So for that I'll just right click and make it none, give the amplitude as 1, click on OK, and then I'll just remove this off, escape, then go to the simulate, go to the edit command, then go to AC analysis, go to type of wave, that is decay. The number of decays is nothing but 0.005. This is one start frequency. Stop frequency is nothing but 100k. Click enter and place it over here. Now run. So at the output side, you are getting a frequency response as well as the phase response. So to know about first the frequency response, at the right side, just right click and click on don't plot phase. So in the frequency response, if I left click to drag it to 1k hertz, I'll just drag it to exit 1k hertz so you all can understand more clearly. Yes. Then again left click to get a second drag and try to get so I got a 10k hertz. Now as you all can see, till 1k hertz your frequency is increasing and it will increase till your frequency reaches the upper cutoff frequency, that is at 10k hertz. After that it will decrease. So this increase is nothing but positive 20 dB per decade, and then it goes on decreasing. So I'll just remove and I'll show you all the phase response. Just right click and directly click OK. So you will get the phase again. Then on the left side, right click, don't plot. So this the dotted is nothing but the phase response. So the same thing I've shown over here. This was for the square, triangular, the frequency response I've shown over here. You all can see, and the phase response. Even if I show you about the graph that I have plotted over here, so shown over here, at till the upper cutoff frequency, the frequency is increasing to positive dB per decade, and then it goes on decreasing. So this was about the practical differentiator, and to conclude that I showed you all the different inputs, that is sine gives you an cosine, square gives you an alternating positive negative spikes, and the triangular waves give you a square wave. Thank you.